In the third part of our titration lab, we're going to take a look at a specific type of titration that's known as a weak acid strong base titration. In this part of the lab, there's a couple goals we have to set for ourselves and objectives that we'll try to achieve as we go through the lab exercise. One objective will be we're going to try to determine the molecular weight of an unknown monoprotic weak acid. Second objective for the third part of the lab is we're going to try to determine the Ka value for the unknown weak monoprotic acid. Once identifying the molecular weight and the Ka value for our unknown acid, the next step would be to try to identify which weak acid we have based on matching with the molecular weights that we have for the possible unknown acids and also the Ka values of the possible unknown acids. This would let us identify what the unknown monoprotic weak acid is that we've selected for the lab exercise. First objective in the lab exercise to find the molecular weight of our unknown weak acid. We have to remember that the unit of measure for molecular weight is grams per mole. There's two things we need to know then in order to solve this. We have to know the grams and also the number of moles we have for our weak acid. The grams is something that we'll measure when we weigh out how much of the powdered monoprotic weak acid we put into our Erlenmeyer flask. The number of moles of the acid come from the equivalence point in our titration. Because at the equivalence point we can say that the moles of acid are equal to the number of moles used to neutralize the acid in reaching the equivalence point. To determine the Ka value for our weak monoprotic acid, we'll need to use the Rice strategy. Now, this will be the same thing that we used in the last unit in finding the Ka value for a weak acid. Procedurally in the lab, the setup will be similar to what we've done in the first couple parts. Sodium hydroxide will go into the burette. In the Erlenmeyer flask, though, we're going to have a solution we prepare of our unknown weak acid. For purposes of this explanation, let's call our unknown weak acid HX, and we'd have a solution that's HX in the aqueous form. Using the Rice strategy, this is the equilibrium reaction that will be taking place for our weak monoprotic acid. This is what would be happening in the flask prior to adding any of the sodium hydroxide. To use the Rice strategy, one of the things we'll need to know is what's the initial concentration of our weak acid solution. Now, if you recall, concentration is measured in molarity, which is moles per liter. Consequently, with our unit of measure being moles per liter, there's two things we need to know about the weak acid solution: the number of moles of weak acid and the liters. The moles of weak acid we can obtain from the data we get at the equivalence point. So once again, at the equivalence point, this would be when the moles of acid is equal to the moles of base that have been added. The liters, on the other hand, with our weak acid solution, we have to measure how many milliliters is the volume of the solution that we prepare of the weak acid prior to adding any of the sodium hydroxide. So in this part of the lab, it is important and critical that we know how much water is used to dissolve our powdered monoprotic weak acid. The volume of the water would be used to give us the liters, which we use to get the initial concentration of the weak acid solution, which is measured in moles per liter. Another piece of information we'll need to get our Ka value in order to be able to figure our equilibrium quantity of each one of our chemicals is the H3O plus concentration. Now, the H3O plus concentration we can obtain by measuring the pH of our weak acid solution prior to adding any of the sodium hydroxide. So a key thing will be we must measure the pH of our weak acid solution before we add any sodium hydroxide. That'll allow us to get the hydronium concentration. That gives us the hydronium concentration, which also gives us the X minus, and we get the equilibrium quantity for all of our materials, which we can then use to calculate the Ka value for our weak acid. As in part 2 of the lab, for this part, we're also going to generate a titration curve. This would be specifically what's known as a weak acid strong base titration curve. When it says weak acid first, that's material that's in the flask. The strong base would be the material that's going to be in the burette. The titration curve is the pH, and this is a measure of the pH that's in the weak acid flask versus the milliliters of NaOH that have been added. So it's graphing as we open the valve and start dribbling sodium hydroxide into the weak acid solution. As time goes by and we add more and more sodium hydroxide, what happens to the pH of our weak acid solution? It also will let us graphically identify the equivalence point for the titration. Because our solution is a weak acid solution, the initial pH typically can be 2.5, 3, even 4 for the initial pH. The reason being that for a weak acid, not all of the acid dissociates to create hydronium ions, so the number of hydronium ions is going to be fairly small. Because of that, the initial pH of the solution is going to be fairly high, at least compared to what would be the case for a strong acid. If we take a close-up look at what's taking place in the weak acid solution, we can follow and understand what takes place when we generate our titration curve. The equilibrium for the weak acid will be taking place in the solution. This would be the weak acid equilibrium for an aqueous solution of a monoprotic weak acid. Now, drop by drop, we add sodium hydroxide from the burette. As the sodium hydroxide drop goes into the weak acid solution, we place into the solution aqueous sodium ions and aqueous hydroxide ions. The hydroxide ions react with the hydronium ions to create H2O and H2O. What this does is it's neutralizing the acid by eliminating the hydronium ions. Now, using Le Chatelier's principle, as the hydronium concentration starts to go down, our equilibrium needs to shift to the right to replace the now missing hydronium ions. By shifting to the right, that causes the amount of weak acid to go down. We start generating salt ions, the X- conjugate base ions increase, and by shifting to the right, we replace the H3O plus ions that just got taken away by the hydroxide ions reacting with them. A consequence of all this is as we continually add in sodium hydroxide, the amount of HX keeps going down and down. The amount of salt solution keeps going up and up until eventually we reach a point where all of the HX is gone. We can no longer generate any additional H3O plus ions, and we would say at this point, when the moles of base we've added is equal to the moles of acid, that our solution is neutralized. At this point in time, the only thing we'd have present would be the sodium ions from the base and the salt ions from the now neutralized acid. And all of the HX would be gone, and we'd reached our equivalence point. Graphically, what this would look like is as we drip in sodium hydroxide, the pH of the weak acid solution is going to stay fairly constant because the reaction keeps shifting to replace the hydronium ions that get taken away by hydroxide, keeping the amount of hydronium fairly constant. Eventually, in the span of a couple drops, we neutralize the last little bit of acid, the pH rises rapidly, and then levels off when we now have an excess of base present in the solution. We can now use our graph to identify the equivalence point. We take the break point for when the titration curve goes vertical and then where it levels off horizontally again. The midpoint halfway through this vertical section would be the location of our equivalence point. At the equivalence point, the only thing we have remaining in our solution is just salt and water. In this case, our salt would be NaX, and then we'd have the water present. Now, one thing we can look at here is the equivalence point. When we have only salt and water here, is a pH somewhere. Our pH is going to be greater than 7 because the conjugate base of our weak acid that we just neutralized has the capacity to generate hydroxide ions, making this particular salt a salt that's going to create a solution that's basic. Since at the equivalence point all we have present is salt and water, the pH here would be whatever the pH that the salt would create when it's put into water. At the equivalence point, our salt would have the conjugate base X minus, and all else that's present in the solution is water. The reaction that would take place would be the conjugate base of the weak acid, or our salt ion, X minus, would react with the water, and by reacting with the water, it generates hydroxide ions. Because we're generating hydroxide ions, this is a salt solution that's going to be basic, and we can observe this by our pH at the equivalence point, where our pH is something that is greater than 7. In fact, for this titration, it looks like it's about 9.5. Now, some key features in a weak acid strong base titration curve. Our initial pH tends to be something a little bit higher. It can be 2.5, 3, 3.5, or 4, because a weak acid does not completely dissociate. So the number of hydronium ions created is fairly small. So the pH is a little bit higher than what we would see for a strong acid. The equivalence point in a weak acid strong base titration is going to be something where the pH is greater than 7, because the conjugate base of the weak acid, which is the ion in the salt, has the capacity to generate hydroxide ions. So we have a pH at the equivalence point greater than 7. It would be whatever the pH should be that's caused by merely making a salt solution of the salt that's present and water. Now, taking a look at two different titration curves. One is a titration that's a weak acid strong base, the other a strong acid strong base titration. Some key features. If we look at the strong acid strong base titration curve, our initial pH is fairly low. The pH stays very low for a period of time. Then we have our break, and if we look at this, the equivalence point for the strong acid strong base titration is going to have a pH equal to 7, which is neutral. Reason we have a neutral pH at this equivalence point is the salt from a strong acid strong base titration will always have two ions that are spectators. Two spectator ions in a salt give rise to a solution that's neutral, so the equivalence point in this titration will have a pH that's neutral. On the other hand, if we look at our weak acid strong base titration, we see that our initial pH is a little bit higher, and then our equivalence point, which is the midpoint of the break, our vertical break here, the midpoint would fall right about here, and it looks like we have a pH which is right about 9, which is certainly a pH greater than 7, which would be a characteristic of the equivalence point of a weak acid strong base titration. Reason being, at this point all that's present is salt and water. The salt, which contains the conjugate base of a weak acid, that conjugate base has the capacity to generate hydroxide ions when it reacts with water or goes through a hydrolysis reaction. And by generating hydroxide ions, it causes the salt solution to be something that is basic. Let's go through how to use and do a calculation for part 3 of the titration lab. Our first question is asking how many moles of sodium hydroxide were needed to neutralize the acid. The given information tells us that we used 17.0 milliliters of a 0.12 molar sodium hydroxide solution. And once again, our capital M tells us how many moles per liter we have of the sodium hydroxide. We can use this to set up a proportion. The proportion we have, the 0.12 molar, tells us we have 0.12 moles of sodium hydroxide per 1 liter. The amount of sodium hydroxide that we used comes over here where we know we want to find X moles of sodium hydroxide that would be present in our 17 milliliter sample that was used to neutralize the weak acid. Solving for X gives us 0.00204 moles of sodium hydroxide were present in the 17 milliliter sample of 0.12 molar sodium hydroxide that was required to neutralize our acid. The next question, how many moles of acid are present in the sample? At our equivalence point, we know that the moles of acid equal the moles of base. So what we can now say is, because we know the moles of base, that's equal to the moles of acid, so our acid sample contained 0.00204 moles of weak acid. The next part of the calculation, we're going to figure our molecular weight of the weak acid. Now, molecular weight, recall, the unit of measure is grams per mole. We need to know two things to get the grams per mole. The number of grams, which is provided. This is what we weighed out and then dissolved. So we have 0.30 grams of acid. And the moles we now know because it was equal to the moles of base. So we have our grams and our moles for our acid, which will allow us to determine the grams per mole for this particular weak acid. We can use the information to set up a proportion. We know we have 0.30 grams of our weak acid present in 0.00204 moles of the acid. If we know that, we can say, well, then X grams would be present if we had 1 mole of that weak acid. Solving for X gives us 147 grams per mole for this particular unknown weak acid. The next question asks us to find the initial concentration of the acid solution. Now, concentration is measured in moles per liter. To find that, we have to know two things. We have to know the moles and the liters of our weak acid prior to adding any base. The previous calculations, we found that we had 0.00204 moles of acid present in our sample. That's how many moles were equal to the moles of base that we'd added. That provides us with how many moles of acid were present in our flask. The volume comes from, we're told here that we dissolved the acid in enough water to make 30 milliliters of solution. So the volume of our acid solution initially was 30 milliliters. Once again, we can set up a proportion to get our concentration of the acid. We know we have 0.00204 moles of acid, and that many moles of acid were present in our 0.030 liter sample we created by dissolving the acid in 30 milliliters of water. Solving for our concentration, the initial concentration of our weak acid, which we'll just call HX, was 0.068 molar. The next calculation asks us to get the H3O plus of the acid solution. We measured the pH of the solution prior to adding any NaOH. Our pH was 2.7. We know that pH is a negative log of H3O plus, and the anti-log of negative pH will give us the H3O plus concentration in our solution. Solving for the H3O plus, we have our H3O plus concentration in our weak acid solution is 2.00 times 10 to the negative third molar. The next question, to get the Ka value for our weak acid, we'll need to utilize the Rice strategy. What we now know from our previous two problems, the initial concentration of the weak acid solution is 0.068 molar. And we also know that the hydronium concentration is 2.00 times 10 to the negative third molar. This allows us to fill in the other spots in our Rice strategy. Initially, before the acid dissociates, the amount of hydronium in X minus is 0. Since we know the hydronium concentration at equilibrium is 2 times 10 to the negative third, that gives us the size of our change value. Because the X minus and hydronium are in a 1-to-1 ratio, also with the weak acid, it's 1 to 1 to 1, we know the size of our change for each part of the chemical equilibrium. So we now know all of our equilibrium values. We can plug these into the Ka expression and determine the Ka value for our unknown weak acid. Solving for the Ka value, we end up with 6.06 times 10 to the negative fifth for the Ka value for our weak acid based on the data that we collected. The next part asks us to get the Kb value for the conjugate base of the weak acid. We can utilize the relationship that Kw is Ka times Kb for an acid and its conjugate base. Calculating, we get our Kb value of 1.65 times 10 to the negative 10 for this particular weak acid conjugate base pair. The next part in our calculation is saying, what's the pH if we were to calculate it at the equivalence point in our titration? Now keep in mind, at the equivalence point, the only things present are salt and water. Consequently, the reaction we're going to have will be the hydrolysis reaction for the conjugate base of our weak acid reacting with water. We can set up and use the Rice strategy with the hydrolysis reaction that's taking place. Our salt is going to be the conjugate base, the X minus, reacting with water. It's going to generate HX plus, the key thing, make hydroxide ions, which causes the pH at our equivalence point to be basic. Our concentration of the salt, though, is going to be the moles of salt present at the equivalence point per the number of liters present at the equivalence point. Consequently, the volume is going to be the volume of the acid solution plus the volume of base utilized to reach the equivalence point. So the volume of our salt solution, it's the 30 milliliters of weak acid plus the 17 milliliters of the sodium hydroxide that were added in order to reach the equivalence point. So the salt and water solution that's present has a volume of 47 milliliters. Now another thing is, at our equivalence point, we know that the moles of acid equals the moles of base. Now what all the acid is turned into at the equivalence point is salt. So if we know how many moles of acid we have when we started, that also gives us how many moles of salt are going to be present at the equivalence point, because all of the acid that's been neutralized, when it's neutralized, it's turned into salt. So if we know our moles of base that we added to neutralize the acid, that tells us how many moles of acid were present in our sample. That also then gives us how many moles of salt are present at the equivalence point. So here's what we now know. We have 0.00204 moles of salt, which is the same as our moles of acid, which is the same as the moles of base added to neutralize the acid, and it's present in 0.047 liters. The volume being the initial acid volume plus the volume of sodium hydroxide that was required to neutralize the acid and turn it into salt. Solving for how many moles we have present in 1 liter gives us our concentration of the salt solution. This comes out to be 0.043 molar of our salt solution. This is the value in our Rice strategy that we can now put in for the initial concentration of the salt solution, which is what's present and reacting with the water at the equivalence point. Initially, we're going to say there's 0 hydroxide and HX before the salt reaches equilibrium. We don't know what our pH is, so this is going to go up by X. And this goes down by X because our reaction is a 1-to-1-to-1 reaction. We have our Kb value from the previous problem, 1.65 times 10 to the negative 10. Because this is so small, our value of X here is going to be very tiny, which allows us to drop the X off. We can now use our Kb value. We can solve for X. X will give us the hydroxide concentration, which we can use to get the pOH and then the pH. Solving for the hydroxide concentration, we get a hydroxide of 2.66 times 10 to the negative 6, which allows us to get the pOH equal to 5.57, giving us a pH at our equivalence point of 8.43.